All right, thanks, Alex. Yeah, always better. So yeah, my presentation is also very high level, building on Simon's. So I'll take you through some high level elements related to hydrogen, maybe a few new points. And then at the end, I was asked to do a bit of blue sky thinking. So, you know, what's all this hydrogen network issue? What's it going to look like in 2050? Is hydrogen going to be relevant? How does it link to gas and all the infrastructure we're building today and things like that? So I've done a little bit of blue sky work and I'll share it with you. It's very much my my opinion, so I'm not going to tag this on any company or policymaker. Next slide, please. This slide is similar to Simon's in that the key point here is, in order to meet the challenge, the 2-degree challenge that we're up against, we're going to need all of the tools in the toolbox. There's no silver bullets. Hydrogen is one of those tools, and it's emerging as something of greater interest for many countries because it has a lot of interesting characteristics. One is the energy density characteristic that Simon talked about. The other is that it's plentiful. It can be manufactured from some of the most common elements in the world, water and fossil fuel or natural gas. Those technologies are relatively known. On the left, I might correct this chart. It shows that today we're at 386 ppm of CO2 in the atmosphere. We're actually at 409. So this chart was pulled from something a few years back. So we're at 409, we're squeezing up, and thus all the focus on the climate issue. Next slide, please. This slide I took from Shell's Sky scenario. And if most of you may be familiar with Shell's scenario work, but in 2018, they did a scenario called the Sky scenario, where they actually did some blue sky thinking around what would it look like to get to the net zero. Now, in that analysis, they showed a pathway to net zero by 2070. And of course, now the focus is very much more around 2050. So this is a few years old, this analysis. But in here, it shows the world's energy system and a few points from this chart. The transportation sector across the top, you know, shipping, cars, heavy transport, aviation, busing, all of those things, those transport fuels all coming from oil products. And so we'll look in, essentially the next slide shows a snapshot of 2070 and maybe how we would achieve those transport motives with other energy sources. The other point here is that electricity is, you know, continues to come a lot through coal. We know that even today, 70% of the world's energy is being met by the 3 major fossil fuels: coal, oil, and gas. And of course, that will have to change by 2050 if we're going to achieve net zero. But a lot of the electricity is still coming through coal, although there's a greater focus on that, and particularly in countries in Asia where they're growing economies and only a source of natural resources are coal. And then we get into the other energy sources: nuclear, biomass, solar, all of interest and all low carbon, but all with their own sets of issues that need to be managed. I think that's all I want to say about this slide. Next slide, please. Oh, maybe in that previous slide, the only thing that also worth noting, hydrogen is a little blue flame, which we see now in, going back, Shanda, going back. Yeah, there's a little blue flame on the little bar chart down the side, hydrogen, and we don't see that anywhere really in today's energy system, but it is used. Hydrogen is predominantly used in industry for manufacturing of ammonia and cracking of oil and methanol. Those are the sort of the primary uses. Next slide, please. Hydrogen. So then in this slide, this is a view in 2070, and we see that the transportation sector across the top has changed significantly. So instead of being all red, now I would argue in 2070 that we would want to likely see even less red here. So for example, shipping could entirely be hydrogen and hydrogen fuel cell driven, or partially electric. So I would argue that the ship could be more blue, light blue, and less red in the future. When we get into the other transport sectors, the light vehicles, the view very much, and it continues to be, that that'll be straight electrics. We'll go to electric cars with batteries. We have the energy density to do it. There may be some hydrogen fuel cell cars and biofuels cars, and of course hybrids over the interim. But in the future, the heavy transport, the trucks, dark blue, and here they're showing actually still some red, but I would argue there'll be a lot of hydrogen. I would argue that second truck that we see up there could be all light blue. It could be fuel cell electric driven vehicles. They have the energy density with the hydrogen and the hydrogen fuel cell drives. The airplanes and aviation, although they're showing hydrogen here, I would argue this could be what we call low carbon fuels, where we're manufacturing fuels from biomass or DAC, shall we say, direct air capture of CO2, and combined with zero carbon hydrogen to produce fuel that could be used for aviation. So it becomes carbon neutral fuel. And then we get into the energy system a little further. I know down below you'll see the buildings all more and more electrification, which is the dark blue. And so this is essentially their scenario. But the hydrogen, I think maybe the point here is the role of hydrogen, significant role in the transport sector, particularly heavy transport, trucks and ships, and possibly even aviation with low carbon fuel manufacture. Also in industry where it could be used directly for thermal energy. In the transport motive, I think it would be more used as a fuel cell. So the other interesting thing about hydrogen is it's not only can be combusted, but it can be used as an energy source in a fuel cell and fuel cell drive, which of course means you have electric motors, is producing electricity on the vehicle, for the vehicle. Next slide, please. I did look to the Zen Study, which was a study for British Columbia done in 2019. And they did talk a little bit about their vision for hydrogen in BC's energy transition. And this is essentially their puzzle. 15.6 million tons of CO2 per year is roughly 25% of BC's carbon footprint. So the feeling here is for BC that we could achieve, hydrogen could provide up to 25% of BC's energy needs. And of course, if that's zero carbon or low carbon hydrogen, then of course could contribute to 25% reduction. It's also worth noting, however, that 1.45 megatons of hydrogen per year, when you're manufacturing that, there's Simon pointed out the different methods of manufacture. Green hydrogen is through electrolysis of water, blue hydrogen through steam methane reforming of natural gas, and pyrolysis of natural gas, which I'm going to talk about a little bit in the next slide. But all methods are likely needed to produce this amount of hydrogen. And one of the statistics I had was that for 100,000 tons of hydrogen, so roughly less than 1/10 of that, you would need 700 megawatts of electricity, making it by electrolysis. So clearly we would need a lot of electricity to make this amount of hydrogen just by electrolysis. So we would need we would need more than 7 gigawatts of power. So yeah, so there's definitely a need for all methods of manufacture hydrogen to try and hit that sweet spot, both on cost and the ability to produce it. They talked about up to 45% hydrogen in the natural gas grid. I think people are still doing the homework on that to determine what the safety, what the level of safety is for the metallurgy. I think it would very much depend on the age of the pipe, the specifications of the pipe, all kinds of different things. And then of course, fuel cell electric vehicles. This is, I think, the place for hydrogen is for the heavy transport, rail, trucks, ships, and then possibly even planes, but that's as a liquid fuel. And this study did talk about export of hydrogen, but I'm not really going to get into that. Next slide, please. This is essentially where they would see the hydrogen being utilized for British Columbia. The pie chart on the right is the 2050 view, and where most of it's being used for transportation, as I mentioned, some in the heavy industries, and some purely replacement of natural gas. Next slide, please. This slide is a compliment to Simon's, and he talked about manufacturing hydrogen from water. So our electrolysis methodology, whether it's wind and renewables, we would need renewables to make green hydrogen. But when we get to blue hydrogen, there's different kinds of blue hydrogen. So there is steam methane reforming of natural gas, which is the one that's most commonly known and commercial operation today for industry. But there's other types of blue hydrogen, both thermal, plasma, and catalytic pyrolysis. And what this is all about is essentially it's taking natural gas and in the absence of oxygen, decomposing the gas into hydrogen, which would be a gas, and carbon, which would be a solid. So it would be in the form of what we call carbon black. So instead of having, where in steam methane reforming, you have CO2 as a byproduct and it's in gaseous form. When we're doing pyrolysis, we have solid carbon black. It's a black powder, basically. So you would have the hydrogen, and then you would have the black carbon powder. So this is another method of producing hydrogen. It is not commercially proven. It's in small scale, but it has been done since the early 1900s. And it was interesting that in some of the hydrogen strategies that we see emerging around the world, they are calling for throwing massive resources at this technology. And because with this technology, it would be easier to dispose of the solid carbon. We could use it for other components, paving roads, and sequester it that way, or carbon fiber products. So there's other ways to use the carbon and sequester it and not have to deal with it in a CO2 in a vapor form and putting it subsurface geologically, which becomes then very it becomes very geology driven. So steam methane reforming of natural gas to hydrogen is great if you have the subsurface geology to put the CO2 away. Whereas pyrolysis, you're not restricted with the geology of the day. You would have a solid carbon waste, which you would then either have a use for, or you would have to dispose of it, perhaps in an old mine or a cavern of some kind. If you're going to go to solid waste disposal. So a lot of work in that pyrolysis area. And I think to me that one opens up a lot more thinking around the whole hydrogen transport question. We heard in the previous presentation and discussion that hydrogen transportation could be double the cost of hydrogen production. So you'll see in my blue sky where I talk about, well, maybe we don't need new hydrogen transportation system. Natural gas is our carrier for hydrogen molecules. And when it gets to its end use, we convert it to hydrogen by pyrolysis. And so that we've already got the transportation system, we're actually building that today with our natural gas infrastructure. So you'll see that in my presentation coming up. But these are, but very, very interesting area, the pyrolysis. There's actually, incidentally, there's a number of companies in British Columbia working on this and making good progress on, I think they're called thermal pyrolysis, pulse pulse methodology. So what happens when you make the hydrogen, the carbon black tends to coat everything up. So you have to do it in batches. You'd stop production, you would clean out the carbon black, and then you would continue with the production. So it's what we call a batch-wise process. They called it a pulse production. Next slide, please. And this is from the Zen Study, where it shows, Simon actually showed this already in his chart, where we have the lowest cost hydrogen, of course, is gray hydrogen, which really isn't what we're looking for today. We're looking for low carbon hydrogen, and we're looking for low cost hydrogen. So, which is also what we need in order to make this breakthrough in terms of hydrogen as an energy source. And you'll see in here that the steam methane reformer and CCS, which is the fourth bar over, is what's commercially proven today. And on either side of it is the thermal and plasma pyrolysis. So the thinking is, but again, it has not been commercially proven. So, but the thinking is based on energy needs and energy inputs, this will be relatively low cost hydrogen as well. The electrolysis, again, is based on technology of the day. So although they're showing much higher cost, those costs could come down significantly as we invest more money in electrolysis technology as well, which has to happen as well, I believe. So we will hopefully see all of these costs coming down, and we would then have a variety of options because we're going to need all the options, not just any one. Next slide, please. This is my shot at blue sky 2050, and I think I was taking it from the perspective of maybe, we're in the business of LNG and natural gas in Canada. We are abundant in natural gas, and what are we going to do with this resource? Does it still have a role as we go forward? We know the IEA has an annual report, which now includes a 2050 scenario, incidentally. And I would note that in their 2050, they show how the coal gets phased out, and even oil, the role for oil continues to diminish, but it doesn't completely disappear because there are things that we just can't make or manufacture without oil. So it continues to have a role largely around feedstock of material for manufacturing, and natural gas continues to have a role similarly. But they really don't talk about natural gas as a feedstock to hydrogen and even as a hydrogen molecule mover. So that's where I get into this, where I say, here's my scenario: global energy demand has continued to grow, call it in 2050, but it's certainly plateauing as energy efficiency becomes a greater focus. China is the world's largest energy consumer. We all know they're predominantly a coal-based energy, but they're on a path to decarbonize, and but they are very much an energy importer. They continue to import LNG. We know that's growing and now and over the next 10 years. In 2050, they'll continue to, this vision says they're continuing to import LNG and other natural resources from Canada. They are not yet at net zero. Their goal is 2060. Their pledge at this point is 2060. So in 2050, they're still on their path to net zero. LNG and natural gas and other resources from Canada are important to them. 2050, Canada has achieved its net zero CO2 goal, which would be quite something. Our grid is carbon neutral. This is an advantage we have today. Canada's grid is, I think it's about 75 to 80% carbon neutral today based on renewables, hydro, and nuclear as we stand. So, this is one area we could achieve net zero with the growth of renewables and others. We could hit net zero on our grid. We have been able to integrate hydrogen as an energy source into the Canadian economy, and this vision has it at 25% of energy needs. used mainly in heavy transport. We think about the distances we were moving materials like trucks across the Trans-Canada, rail across Canada. Those have all been converted to either hydrogen fuel cell or some other carbon neutral fuel. Probably the light trucks could go purely electric. Industry is another area for hydrogen. It's used for thermal energy, and commercial buildings actually might be a bit of a mix between thermal energy and electricity, particularly where the grid is more challenged to supply zero carbon electricity. A mix of blue and green hydrogen production, depending on the location. So in the west, in the Western Canada, where we have good geology, there's an opportunity for blue hydrogen with CCS, and in the east of Canada, less so. So they would be looking more to electrolysis. And then, of course, the idea of pyrolysis. If we're moving natural gas around the country, we could convert it to hydrogen at its specific locations. So another way to get hydrogen to the east as an alternative to electrolysis. Local hydrogen hubs. I think this is a key, that the hydrogen manufacturing then has its own, shall we say, pipeline network that's local. And those pipelines would be hydrogen specific, so designed for hydrogen, which is at this point a high stainless steel alloy type piping. However, hydrogen distribution on large distances, let's say we wanted to move energy across the country as we do in the Trans-Canada pipeline, well, this could be, that's the next point, the long range hydrogen, that we would continue to use our natural gas transmission and then convert it to hydrogen at the location or the hub that it's needed. So that's my view of how the hydrogen distribution evolves. BC is a global leader in the export of not only, zero CO2 LNG, but many other natural resources. We're exporting copper, zinc, we're exporting many products, aluminum, and all of these things we're leading the world in terms of performance on carbon intensity. So this is good news. LNG continues to be exported to Asia. It's used directly for their energy needs, and it's converted to blue hydrogen over there. So they can make their own hydrogen by electrolysis, but if they want to make hydrogen through a blue path, they need the feedstock. So again, we move the feedstock, continues to move as LNG rather than converting it in Canada and repurposing all our ships. And then the global shipping is with hydrogen fuel cell technology and electric drives. So we're going zero emissions on the shipping. Next slide, please. And then we get a little more local. So BC's ports, let's call it Kitimat, Prince Rupert. We'd built out an LNG an industry there, and they're continuing to export LNG to countries that have evolving energy transition. And they can use the LNG either directly as natural gas or convert it to hydrogen. All ports are equipped with hydrogen manufacturing because ports are hubs for rail, for trucking, for shipping. So all those ports would have hydrogen manufacturing, and it depends on the technology of the day, but I see it as a mix of green and blue hydrogen in the ports. BC Transport has moved to the use of hydrogen and fuel cell electric drives. And because we've been able to build out the fueling system for hydrogen, we start to see some of the growth in hydrogen for the light vehicle transportation as well, which actually stretches out the distance. So we know, for example, the limiting factor for electric cars is the size of the batteries and the mass, and then that then limits the distance they can go. If we can go to hydrogen and fuel cell electrics, maybe we get 1,000 kilometers out of a tank. BC Industry the Lower Mainland has a local hydrogen production. It's largely focused in around green hydrogen and a local hydrogen distribution network. And I added in a large scale CCUS hydrogen DAC and future fuels hub for BC. And this is one of the things we see. These hydrogen networks are going to need hubs, and the hubs, in this case, if we have a CCS hub in central BC where we could sequester CO2 from pulp mills, refineries, all kinds of things, it creates then a center for blue hydrogen production. And then it even creates an opportunity to capture CO2 out of the atmosphere by DAC, and even put away CO2 right out of the atmosphere into the subsurface to try and, again, to net zero, we're going to need all the tools in the toolkit. And then the future fuels is the combination of hydrogen and CO2 that's been captured from a carbon neutral source. So whether from the atmosphere or from biomass. And we can combine those two products, CO2 captured from the atmosphere or biomass, and hydrogen produced as low carbon hydrogen, and produce fuel that then becomes carbon neutral. And I see that would be a fuel for aviation and those harder to decarbonize transport sectors. And then buildings could be a mix, largely electricity. However, fuel cell electrics might be something, particularly in remote communities, but also in areas that are might have limited access to grid. Anyways, that's my blue sky stuff, Alex and Shanda. Throwing in the hydrogen was really very focused on hydrogen. That's what you asked me to do. This is all really just to create conversation and stimulate discussion. So I'm happy to take questions.